Welcome everybody. The Department of Physics and Astrophysics at UND would like to wish you a warm welcome to our virtual colloquium today. This colloquium is hosted by our department in coalition with the physicists, in collaboration with the Physicists Coalition for Nuclear Threat Reduction, which is a part of the APS Office of Government Affairs. I'd like to welcome our distinguished speaker, Dr. Stewart Prager. He is a professor of astrophysical sciences at Princeton University, an affiliated faculty member with the program on science and global security, and he used to direct the Princeton Plasma Physics Laboratory. He's done things like directing the Madison Symmetric Torus Experiment and the Center of Magnetic Self-Organization in lab and astrophysical plasmas. So he's an expert on plasma physics and fusion energy, but he is also an expert on nuclear threat reduction, which will be the topic of today's colloquium. After the colloquium, the talk will be about 50 minutes. There'll be a 10-minute question and answer session. And then Dr. Prager will lead a discussion for anybody who is interested of the Physicists Coalition for Nuclear Threat Reduction and opportunities to get involved. So it's probably physicists who are more than anyone else to be thanked for unleashing the power of the nucleus. And it is also our responsibility. So this is about taking responsibility for what we started, I guess. So over to you, Dr. Prager.
Okay, yeah, thanks very much for that introduction and those last few comments. I appreciate that. Let me just go to full screen here, and let me get a laser pointer. Okay. Okay, well, thank you for coming to this presentation. As said, today I'm going to talk about the situation with regard to nuclear weapons in the world. And the reason I'm speaking about this is because it's an important topic, and I think it's important to most physicists. This colloquium will be a little bit unusual because this problem, really the problem of nuclear weapons in the world, is at its core, it's not a scientific problem, it's really a policy problem. So I'm going to be talking about policy as well as some technical aspects. As was said, this is triggered by a new APS project, which I'm here as part of. And also here actually is someone from the APS Office of Government Affairs, Charlotte Selton, who will be available to chat informally for those that are interested after this colloquium. So let me get started. The motivation for this talk, I think, is well known to all of you. It's that the nuclear arms threat is as extreme as ever. We still live in a world that where a few men can kill pretty much everybody on the planet by pushing the buttons, and they can do that very quickly. This is not a situation that is stable. It's unstable, and in many ways it's getting worse. However, this is a man-made threat, and since it's man-made, we can also reduce this threat. But it's off the radar of the public. The public isn't really paying much attention to this threat because it's an invisible threat. And so we feel that the physics community can play a special role in advancing threat reduction because we have a special relationship, as was just said, to these weapons, and thus our voice can be particularly influential. So what I'm going to do today is review some, basically this is a review talk, where I'm going to review some technical aspects of nuclear weapons. Maybe for many of you it'll just be a reminder. Review some policy aspects. I'll comment on what I think can be viewed as a current crisis in the nuclear world order. And then I'll close with a couple of comments of what the physics community can do through this new Physics Coalition for Nuclear Threat Reduction that's sponsored by the APS. And I should mention at the outset that if in today's colloquium and discussion I express any opinions, those opinions are just opinions of me alone, and they don't represent the APS necessarily. It's interesting to me to virtually be here in North Dakota. You may actually have an appreciation for this issue and an understanding of this issue that exceeds that of most physics audiences, because in North Dakota, as you know, at the near you in the Minot Air Force Base, there's, I think, somewhere about 130 intercontinental ballistic missiles that are tipped with nuclear warheads, ready to be launched in minutes. So this is a topic that I'm sure many of you have been engaged in, and is particularly relevant to you considering your location. So let me begin just with reviewing a little bit of the facts about the enormous power of the fission chain reaction. And here, shown in a cartoon, is just a single fission reaction. Imagine that a neutron bombards a uranium-235 nucleus, excites it, and then fissions into two product nuclei, krypton and barium, plus, in this example, a few neutrons. So what has happened here is that one neutron has multiplied into three, and the neutron energy, which might have been about 1 or 2 MeV, got multiplied. The kinetic energy of the products is about 200 MeV. So there's a multiplication of the number of neutrons and a huge amplification in energy. And one can put this into a chain reaction. If one has, instead of just one fissile nucleus, a large number, then you can get a chain reaction where one neutron bombards a nucleus, it fissions into two, and in this cartoon example produces 2 neutrons, which then produce two more fissions that then produce 4, and so on. This is a very rapid and powerful process. You can fission 80 generations, that's 2 to the 80 nuclei can be fissioned in just 1 microsecond. And that would fission about 1 kilogram of fission material. And it would release an energy which is equal to about 15,000 tons of TNT. So in nuclear weapons, one measures typically the explosive power by comparing it to that of an equivalent amount of chemical explosive TNT. So nuclear fission is about 15 million times more powerful than TNT. But you need enough nuclei to get a critical mass. You have 2, 10 is not enough, you need a large number. How many you need to get a critical mass for a supercritical chain reaction is a neutron transport problem. It's not a difficult problem. The neutron production rate by the fission reactions have to exceed the neutron loss rate by collisional diffusion or absorption by nuclei. So it's a neutron transport problem. The critical mass can be reduced if one puts a reflecting boundary around the assembly of fissile material, so the neutrons are reflected back. And if one does the calculations, you can find that the critical mass for a very fissile material, plutonium-239, is about 5 kilograms. U-235 is not quite as fissile and doesn't produce quite as many neutrons, so it's a little bit higher. About 15 kilograms of U-235 will give you a chain reaction. Well, this chain reaction has been weaponized, as you know. Here's a picture of the simplest kind of nuclear weapon, nuclear warhead. It's a gun-type fission weapon. I'm going to show you just cartoons. I have not ever seen a nuclear weapon, and I haven't worked on them, so I only have a cartoon level knowledge of it myself. But the way this works is one has 2 subcritical masses of U-235 shown here in blue. And it operates like a gun. A chemical explosive then propels the left subcritical mass down this barrel, and then it mates with this other subcritical mass like a gun. So when the 2 subcritical masses mate together, they then are supercritical, and you get fission explosion. it uses uranium. Plutonium wouldn't work here. It's too slow for plutonium. And plutonium is 239 is often contaminated with plutonium-240, which through spontaneous neutron emission will cause this to physically get premature fission. So this works. It's not efficient. Only about 1% of the uranium actually fissions. But it was used in the explosion over Hiroshima in 1945 without even a prior test. It's so simple and reliable. But it's inefficient, and a more sophisticated and complicated and more efficient fission weapon is an implosion type. And an implosion type, you reach supercritical mass density, not by a gun mechanism, but by an implosion mechanism. So one has shown here a hollow pit of plutonium fuel, and the pit is caused to implode. And as it implodes, its density increases and it becomes supercritical. And it's imploded by a ring of chemical explosions that go off in a careful way to excite an inwardly imploding spherical shock wave that implodes this plutonium pit. The plutonium pit implodes, and when it's at a certain point of implosion, it triggers a neutron source that then gets all the chain reactions going. This is done with plutonium. It's a very rapid compression. It's more efficient than the gun type. About 15% of the plutonium was fissioned when it was used over Nagasaki, Japan, 3 days later in 1945. This did undergo one test in New Mexico a few weeks before being used in World War II. But modern weapons today are yet more complex and yet more powerful, and they involve two stages, a primary and a secondary stage. The primary stage is just like I've shown you, with one little wrinkle. There's a DT boost gas, which you get DT, deuterium-tritium fusion, that generates neutrons that makes the fissioning more efficient. And there's a secondary where most of the explosive release comes from fusion reactions as opposed to fission reactions. The fusion reaction fuses deuterium and tritium nuclei, produces an alpha particle and a neutron. And here too, there's a big multiplication in energy from the parent nuclei to the neutron and the alpha particle. Deuterium comes from seawater, but tritium isn't found in nature. So it's actually bred in the warhead itself. It's generated in the warhead by placing lithium in the warhead, and then lithium, when it's bombarded with a neutron, will produce an alpha particle and a tritium nucleus. So it's an interesting configuration, and the way that works is that the fission bomb goes off the primary, and its main purpose here is to generate X-rays. And X-rays, high energy X-rays, bathe this cavity. The X-rays cause this red shell of uranium to ablate, and because of the ablation and the rocket effect, the shell implodes, and it causes the fusion fuel, which is in the form of lithium deuteride, to implode. That implodes, and it rapidly heats up and turns into a plasma. Then a uranium spark plug, it's called a spark plug if you like, uranium fission is triggered in the center. That generates neutrons. The neutrons, through the lithium, breed tritium. You then have deuterium and tritium here. That gets very hot through the compression, and you get a fusion reaction. So it's a fission fusion bomb. And the yields of such a bomb are enormous. And let's compare it again to chemical explosions. The largest conventional, that is non-nuclear conventional weapon, has a yield of about 11 tons of TNT, large mass of TNT. The Hiroshima bomb was 15 kilotons, about the equivalent of more than 1,000 large conventional bombs. A typical warhead in the US arsenal that might be found up the road from you is on the order of 300 kilotons, which is about the equivalent of 20 Hiroshima bombs. The largest nuclear detonation ever made as a test was made by the Soviet Union in 1961 over the ocean north of the Soviet Union, and it was a 50 megaton blast, which is inconceivably large. I think 600 miles away from the blast, it blew out window panes in buildings. So this is quite powerful. What are the effects of a single bomb? Well, clearly the effects have been known for 70 years, frankly, since they were used in Japan. What's new, if you want to say call it new, is that we're still living with this threat 70 years later. The effects are multiple. About half of the energy comes out in the blast, mechanical energy in the blast waves that are generated from the sudden explosion. And blast waves are just the same as shock waves. About a third of the energy comes out as thermal energy, just the heat from the intense heat from the fireball that's produced from the explosion. And about 15% emanates as prompt or delayed nuclear radiation. So this mixture of energy types produces fatalities from the blast itself, from winds generated by the shock wave, from burns, from the thermal flash, from fire, and from nuclear radiation. To give you a little indicator of the physics of the blast wave, imagine that you have a nuclear explosion at some altitude above the ground. And in the Hiroshima case, it was, I think, 1,500 feet above ground. It generates these spherically outward going blast waves or shock waves. Some of them reflect off of the ground, bounce back. As they bounce back, they travel in shock heated air and catch up to the initial wave fronts, so they reinforce it. So it creates huge waves of pressure. And as in a shock wave, there's a steep shock front. So if you plot the overpressure, which is the pressure in excess of the atmospheric pressure, versus distance from the explosion, you can see that the pressure has a steep shock front. So it's a wall of high pressure. And in the wake of the shock front, there is a gradient in pressure that generates the winds. And as it travels, the pressure, the wave attenuates. This front is very steep. I think it's probably sub-millimeter theoretically. What are the effects of a blast wave? Well, if the overpressure is 5 pounds per square inch, it will destroy residential buildings and generate hurricane scale winds about 160 miles per hour. If it's 10 pounds per square inch overpressure from the shock wave, it'll destroy all buildings and generate winds at 300 miles per hour, greater than you get from any natural hurricane. The effect of this blast wave has been measured early. In 1953, for example, the tests were done in the Nevada desert. And here's an example where in the Nevada desert, a 16 kiloton, Hiroshima size, but small in today's standards, a nuclear warhead was exploded. And they measured its effect on a building. The building is 3,500 feet, about 2/3 of a mile from this bomb. And here you can see in picture frames what happens. First, the thermal flash lights up, illuminates the building. And then the heat from the flash starts to set the building on fire. Then you can see the blast starting to arrive, and the blasts arrive, and it just obliterates the building 2/3 of a mile from the bomb blast. This whole exposure is 2.3 seconds, so it's a sort of an instantaneous. In a second or two, the building's destroyed. That's just due to a rather small warhead of 15 kilotons. What happens if you explode an average size warhead at 315 kilotons, let's say at an altitude of 8,000 feet? What happens from the blast? And the blast pressure decreases like 1 over distance cubed from the ground zero. So if you have an explosion here, 2 miles from the explosion point, the overpressure from the blast wave will be 10 psi. So within 2 mile radius of the blast, there's essentially 100% fatalities. Everybody is killed, and there's a near total leveling of all buildings. At 3 miles, you're at 5 psi, about half of the people will be killed. That's the blast, but the thermal radiation dies off more slowly, only dies off like 1 over distance squared. So 3rd degree burns will occur from the thermal radiation at 4.5 miles from the bomb blast site. 3rd degree burns, if it covers more than 1/4 of the skin, it will be fatal. So this, as you know, as you well appreciate already, I'm sure, this is not a war-fighting weapon because it's indiscriminate. It really is accurately described as a weapon of genocide. And there was what will this do? Well, here's a schematic. If you exploded this over the lower Manhattan in New York City, choose a densely populated city in the United States, you can see that 3rd degree burns extend, for those of you that know the New York topography, out to New Jersey and 3 different boroughs in New York. Anyway, it leads to about 1 million deaths and about 2 million injuries. So this one bomb blast of an average sized bomb in New York City would destroy that city and clearly be the worst catastrophe ever to occur in the United States. Well, this has been done once with twice with a small bomb in 1945, which produced a calibration of the effects, a grim calibration, if you like. When this was exploded over Hiroshima, it led to over 100,000 fatalities, mostly from burns, from the flash and fires and falling debris. What it produced a firestorm because the heat and the winds, the heat sets things on fire, the wind knocks down power lines, which causes fires, and the winds spread the fire. So there was a firestorm that spread over 4 square miles. You can see that where there used to be a city, there now is almost none remaining. To give you a sense, another sense maybe of the power of nuclear bombs, this was a gun-type uranium bomb. A plutonium bomb with the same explosive power would have a plutonium pit of this size. This is the size of the fissile material that would do this amount of damage to a city. So this is some description of the physical effects of a single bomb. Since 1945, construction of nuclear weapons has become an industry. They're mass produced, and now where are we today? Today, nuclear weapons are spread over 9 nations. Most of the nations of the world have forsworn nuclear weapons, but 9 nations have them. So in total, there's over 9,000 nuclear warheads in active military stockpiles. Here you can see the number of warheads versus the 9 nations. So they were the 5 nations that were originally had nuclear weapons: Russia, now US, China, France, and the United Kingdom. And then over the years, Pakistan, India, Israel, and most recently North Korea have acquired. And you can see that over 90% of the weapons are in Russia and the United States. And each has about 4,000 active weapons. About 2,000 are deployed, and shown in red here means that they're mounted on delivery vehicles. Another 2,000 in each country are in storage facilities and could be uploaded onto missiles when needed. And about another 2,000 each are waiting to be dismantled and retired. It looks like there's not too many elsewhere, but 200 missiles in the United Kingdom or Pakistan, that's enough to kill many millions of people and have a huge effect on civilization as we know it. So this is where we stand today in a number of weapons. These weapons are spread nationally, but they're also spread across what's known as the nuclear triad. They're spread in land, sea, and air. In sea, they're mounted in submarines, which has an advantage of being survivable, and submarines are not detectable, so they're really an invulnerable strike force, and they're prompt. You push a button and a ballistic missile leaves immediately and moves at Mach speeds of 10 or 20. There are bombers, airplanes. Here is shown one that can carry many warheads. And these are slow, but they have the advantage of being flexible, right? Warheads, airplanes are maneuverable and recallable. If you send an airplane on a mission to bomb with a nuclear weapon and you change your mind, you can recall it. You cannot recall a ballistic missile. And then finally, there are intercontinental ballistic missiles stored in underground silos, which are prompt, but they're fixed targets, so they're vulnerable and they're not survivable. They can be taken out by Russian warheads. And the US has 400, and as I said in the opener, in Minot Air Force Base, I believe there's about 130 of these in underground silos. Well, if you add up the total world arsenal of these 9,000 weapons, it adds up to an explosive power of several thousand megatons, which is an incomprehensible amount of explosive power. It's the equivalent of about 300,000 Hiroshima bombs we have today. By comparison, the entire bombing of World War II totaled 3 megatons, a tiny fraction of what's available today. So these nuclear weapons, you can do the calculation for yourself, can directly kill billions of people if they were used. But that's the direct effects. There are also indirect effects of nuclear weapons. Nonlinear effects, if you like, effects that if you set off multiple weapons will extend geographically and temporally. And the first one is fallout, radioactive fallout. And I know there's been a lot of discussion about that, so I'm not going to discuss that. Another one, which is, I mentioned, but I almost feel foolish mentioning it, is the breakdown of infrastructure of society that happens from a nuclear weapon. The breakdown in healthcare facilities, the breakdown in financial systems, everything. It's so, we talk about the saturation and of healthcare facilities in days of COVID, the hospitals being overrun, not enough ICU beds in the worst cases in some cities. Well, if a nuclear weapon is exploded, the hospitals and the ICU beds will be destroyed along with everybody else, and people that do survive will be left to suffer without any health care whatsoever. To give one silly statistic almost, in the entire US, there are 2,000 burn beds, 2,000 beds, the country's capability to treat burn victims is only to treat 2,000 burn victims. And that wouldn't even be able to treat all the victims in one small town. What I would like to spend some time on is if you set off lots of nuclear weapons, what it does to our climate, and it cools the climate. And this is a very, very serious effect. The disruption of the climate by nuclear weapons. And how does it do that? It does it by the fires that it ignites. Where you set off a nuclear weapon in a city or where there's flammable materials, it sets off massive fires, and the fires produce carbon particles or soot. The carbon particles or the soot are heated by the sun. They then rise into the stratosphere above the earth. And you can see by an artist's sketch that the earth, before nuclear weapons are set off, you get a cloud of carbon, soot, that envelops the earth, spreads around. It then blocks out the solar radiation. The result is that the temperature will decrease and the sunlight reaching the earth will decrease. In the 1980s, this was called nuclear winter. It's studied these days much more effectively because climate scientists have started to study these effects using modern climate science computational models. And I'd like to just cite some recent studies of what would happen if you just had a regional nuclear war. And climate scientists have taken as a particular example a nuclear war between India and Pakistan, 2 nuclear powers that are rivals, and each one sets off 50 Hiroshima-sized bombs. So this would be overall 115 kiloton bombs are unleashed regionally in India and Pakistan only. This would correspond to a detonation of only 0.1% of the world arsenal. So it's a very small nuclear war, limited regionally. it would generate about 6 million tons of carbon soot. And this is what it does to the temperature according to these studies by climate scientists. Here's the temperature from 1880 to the time of the nuclear war. And you can see global climate change, the global warming happening over the decades. Nuclear war then does this. It takes the temperature, and this is the globally average temperature, and it decreases it by more than a degree centigrade instantaneously. And then it takes about 10 years for the temperature to relax back to the pre-nuclear war level. The climate scientists comment, and this is their comment, not mine, that this global climate change would be unprecedented in recorded human history. In the global decrease in temperature is not uniform over certain parts of the globe. It'll decrease by 2 to 3 degrees. The scientists also calculated the effect on crop production of this decrease in temperature and decrease in sunlight. I won't show those results, but global crop production falls. And then there's been a little bit of a look at what this would do, the crop production would do to the production of food for people. And it's been estimated that it would place on order of 2 billion people at risk of famine. So let's step back a little bit and look at this. In the war zone itself, there would be about 20 million people killed in India and Pakistan, an unbelievable amount of people killed in a war quickly. But it would imperil the lives of 2 billion people who are essentially innocent bystanders to this local war. So the number of people killed indirectly, many more than in the war zone. So nuclear war really affects anybody on the globe. So this is what I want to say about the technical aspects. And let me talk about some nuclear policies that I think are unfavorable and destabilizing. And the first one is that many weapons are kept on hair trigger alert. And what do I mean by hair trigger alert? Hair trigger alert means that weapons are postured such that they can be set off within minutes of receiving a launch order and ready to launch in less than 10 minutes. In the world today, about 1,900 missiles armed with nuclear warheads are on alert in underground silos and in submarines, mostly in the US and Russia, split about evenly. This, again, if you do these sums to about 500 megatons of explosive power, which ends civilization. So at this moment, there are enough missiles on alert status in silos that within a few minutes of an order, they can really end civilization. And 400 of them are in underground silos in the upper Midwest where you guys live. Well, this is, many view this as unfavorable because clearly any technical system that can be activated in a few minutes, and I do think we know this, those of us that are experimental physicists, are prone to accident, prone to mistake, vulnerable to a hasty decision. Might also add that the president in the United States, the president has sole authority to launch. At any moment of the day, the president can pick up a phone and issue an order, and within minutes can launch in the United States 850 missiles. Another related policy that I think increases our danger is the launch on warning option that's available to the President of the United States. In both the US and Russia have this launch on warning option. And what does that mean? Well, imagine that a missile is launched in Russia toward the US, it takes about 25, 30 minutes for the travel time. And if we get a warning that a nuclear missile was launched toward us, the president can decide within those 25 minutes whether to retaliate. What does this mean in practice? Look at the timeline. Imagine that there's a Russian launch at t=0, and that a minute later it's detected by infrared radiation by satellites detecting IR radiation from the rocket plume. It takes a few minutes to alert the military takes a few minutes to notify the president takes maybe 5 minutes to assemble whatever advisors he or she wants to assemble. Well, if you want to decide to launch before the ICBMs are taken out, then the president has about 5 minutes to be briefed, for the options to be described and to decide whether to launch missiles. If he decides to launch missiles, then it takes a few minutes to convey the message, another couple of minutes for the missiles to be fired. So maybe by 23 minutes, T = 23 minutes, the missiles are fired and they head toward the Russian silos. And then 2 minutes later, the Russian bombs detonate over the empty silos in the upper Midwest. Unless, of course, this is all done on a false alarm and these missiles were launched by accident. So the threat posed by these ICBMs that are on alert status is that they pressure a president to adopt a use them or lose them attitude to decide to launch them before they're taken out. This is maximally undemocratic. A nuclear catastrophe can be launched in minutes without congressional input or any input from the public. I think I'll skip this. Now, these weapons that are on alert status, I mentioned that they're accident prone. And if you look back in history, we'll see that we have been very, very lucky that there have been no nuclear catastrophe, because there have been many, many known close calls. And I'm going to kind of break from what is a good delivery technique. I'm going to quickly read through a slide to give you a sense of the near accidents that we had. And let me first cover false alarms, false warnings of attack. In 1960, a US radar in Greenland reported dozens of Soviet missiles that were headed toward the United States. The US air defense was put on maximum alert, but it wasn't true. The cause was the radar was fooled by a moonrise over Norway. In 1979, it was reported that a Soviet attack of 200 missiles was detected by a military computer. 200 missiles headed toward the US. ICBM missile crews were put on high alert, nuclear bombers prepared for takeoff. Well, it wasn't a real attack. The cause was a simulation of an attack mistakenly appeared on an operational computer, and it's not well understood even today why this happened. In 1980, the National Security Advisor Brzezinski was awakened at 2:30 in the morning by news, again, 200 Soviet submarine-launched missiles headed toward the US. He didn't wake his wife because he figured in a few minutes he would be dead. Bomber crews started their engine and missile crews opened their safes to get the launch code. It was just a defective $1 computer chip. False alarms the other way. In 1983, a Soviet satellite detected an incoming US attack of 5 missiles. It wasn't real. It was just sunlight reflected from clouds. In 1995, Russian radar detected a US submarine-launched missile to strike in 15 minutes. Russian nuclear forces went on full alert, and President Yeltsin retrieved the nuclear launch code. The cause was just a scientific rocket which was launched to study the aurora. So why didn't these false warnings lead to the president in either country to launch an attack? And the reason is that in all cases, someone didn't bring, in most cases, someone didn't bring the messages to the president. Someone judged or just intuited that the alarm was false. In some cases, they disobeyed procedures to do this. In one case, a US officer did not notify the president of an incoming attack. If he did, the president would have had minutes to decide whether to launch a retaliatory attack. Another example, a Soviet officer who intuited that the response wasn't real did not recommend a responsive missile launch. He was often been referred to as the man who saved the world, and because he violated procedures, he was fired from his position. So we were lucky. There have been other accidents of a different nature, mishaps with warheads. In 1961, a nuclear bomb was accidentally dropped from an airplane 10,000 feet above North Carolina. Fortunately, it didn't detonate. In 1980, there was a chemical explosion in an ICBM silo that propelled a 9 megaton warhead 200 feet into a ditch. Luckily, it didn't explode. There were misplaced warheads. 6 missiles, nuclear missiles, were mistakenly flown from Louisiana to North Dakota without anybody being aware of it for a day and a half. In 2010, there was a gap in control. There was a loss of control over 50 ICBMs in Wyoming for an hour. For an hour, nobody had any, in the US, had any control over 50 ICBMs. And the last thing I'll mention is the 1962 Cuban Missile Crisis. So I'll mention just one aspect of that. And the aspect is the following, that off the coast of the United States and Cuba, there were submarine nuclear submarines with nuclear warheads. A Soviet submarine commander mistakenly thought under the water that war had begun. He decided to fire a 10 kiloton nuclear torpedo against the US fleet. It required the seconding of another officer on board, and the required second officer agreed to launch the nuclear weapon. By pure happenstance, on that particular submarine, the Soviet head of the submarine fleet happened to be on board, and he, for whatever reason, overruled the order. Had he not been on board, this likely would have triggered a nuclear catastrophe between the US and Soviet Union. Well, all this has led General Lee Butler, who was the head of the US Strategic Command in the 1990s, to say, we escaped the Cold War without a nuclear holocaust by some combination of skill, luck, and divine intervention. I suspect the latter in greatest proportion. But this problem is controllable, and there's been enormous progress. So progress can be made. I know I've painted a bleak picture. And let me give some indicators of the progress through some major examples. And one major example of progress is the Nuclear Non-Proliferation Treaty of 1970, which was signed by all except 3 nations in the world. And it's a deal where the non-nuclear weapon states agree never to develop nuclear weapons. And in return, the 5 nuclear weapon states of the time agreed to work toward cessation of the arms race and to nuclear disarmament. From a proliferation point of view, it's been reasonably successful. If you look at the number of countries that have nuclear weapons from 1945 to today, it's gradually proliferated up to the 9, but it hasn't, but it's been somewhat saturated and it hasn't kept going up and up. So it's been successful in that sense. It has set a legal requirement on nuclear weapon states to disarm multilaterally, and this has not been fulfilled. Another successful treaty was the Anti-Ballistic Missile Treaty, which barred the Soviet Union and the US from deploying nationwide defenses against incoming missiles. It limited each country to just 100 missile interceptors, which might be enough to knock out a few coming in, but not enough to protect the homeland. And this was done wisely because if you limit defense, it allows countries to limit their offensive weapons. And this ABM treaty then led to the following. And what you can see here is a great success story up to a point. The dramatic reduction in the number of warheads in the world. Here's the number of warheads. And just look at the gray, which is the total in the world, mainly from the Russia and the US. And you can see the buildup throughout the Cold War to a dizzying 70,000 nuclear warheads in the world. And then there started to be agreements between the 2 countries and a series of treaties that have driven down the number of warheads in the arsenals. The warheads have been destroyed to the level that they are today. We're now at a level which is maybe 15% of what once was. So this is a tremendous improvement. But as I've shown you, this number of warheads is enough to destroy the world many times over. It's still very dangerous. There's been almost no weapon testing since 1996. Before 1996, there were 2,000 tests of nuclear weapons in the atmosphere, underground, and underwater. But in 1996, the Comprehensive Test Ban Treaty was signed. And since 1998, the only tests were in North Korea. There's been a near absence of testing which is a substantial barrier to nuclear weapon development. I don't know if that's, there's a phone ring, and I don't know if it's my computer or somebody else's. Okay, I stopped. What I'd like to mention is nuclear weapon-free zones. This is rather remarkable. There are 6 treaties that establish regions that prohibit nuclear weapons in the world over these regions. And if you look at the map of the world, all of these maps in all of these countries shaded in blue by treaty, nuclear weapon-free zone treaty, have pledged to and do not have any nuclear weapons in them. And all the red countries do. And you can see the entire southern hemisphere is a nuclear weapon-free zone. So countries can act rationally and forswear nuclear weapons. And if you just extend this blue area to the red area, this problem would be solved. And the last thing I want to mention in terms of recent treaties is a treaty on the prohibition of nuclear weapons. This is a treaty that says that nuclear weapons are illegal. In 2017, it was adopted by, at the United Nations by a vote of 122 to 1. However, none of the NATO countries took place in the vote except for one, and none of the nuclear weapon countries took place in the vote. They definitely, essentially boycotted it. So it was a treaty that was signed by about 2/3 of the non-nuclear weapon states of the world. It entered into force just this past January when it was ratified by 50 nations. So of course this treaty only makes nuclear weapons illegal for those that sign it, but it sets a new norm, and in fact, it sets a pressure in the world for countries to head toward disarmament, as the Non-Proliferation Treaty says they should. And the organization that pushed this treaty got the 2017 Nobel Peace Prize. So that's good news, but I'm going to close on some bad news. I'm kind of oscillating from good to bad. The nuclear world order is now in crisis. And this was represented metaphorically by what's called the doomsday clock, which is just a metaphor. It's a clock that's set by a panel within the Bulletin of Atomic Scientists that is a qualitative measure of how close the world is to a nuclear catastrophe. And in 2020 and in 2021, the clock was set at 100 seconds to midnight, which is the closest it's been set since the nuclear age started in 1945, because that bulletin, that expert panel, feels we're slipping into a new arms race. And I'm going to close with just indicating why things are getting worse in a way now. But one, even though the proliferation's been gradual, we do now live in a world that's not bipolar anymore between the US and Russia only. It's multipolar. 9 nuclear weapon states, which means we have n equal 9. There are many, many more scenarios for nuclear war to break out, and many more scenarios for accidents to happen. There's non-state actors, the threat of terrorists. There's the threat from emerging technologies, in particular cyber attacks. This is a major threat to the nuclear weapons complex and strategic stability. You can imagine a cyber attack can provide a false warning of an attack, or it can hide a real attack. It could break the communications between a leader and its military in a time of crisis. And you can even imagine that a cyber attack can enable the unauthorized launch of a nuclear warhead. So this is extremely grave. In recent years, there's been a near collapse, maybe reversing, I hope, but there's been a near collapse of the arms control regime that has driven down the nuclear warheads. In 2002, the US withdrew from the ABM treaty. 2019, the US and the Russia withdrew from the Intermediate Nuclear Forces Treaty. I didn't discuss it yet. 2018, the US withdrew from the Iran nuclear deal. In 2020, we withdrew from something called the Open Skies Treaty. The Non-Proliferation Treaty is under some threat because nuclear states are not disarming, we're rearming, as I'll get to in a moment. Fortunately, the New START Treaty, which caps the number of warheads in the US and Russia, was just renewed about a month ago, which is a good thing, but it was a close call that it was really headed not to be renewed. And the last thing I want to mention in terms of bad news is that we are at the beginning of an emerging nuclear arms race, fresh one. Weapon modernization is now underway in the US and Russia and China. In the US, about $1 trillion is going to be spent over the next 30 years on nuclear weapons, which will commit us to nuclear weapons to the end of the century. And there are new types of weapons and new types of defenses that are being launched in these countries. And so we are right now embarking on an emerging new nuclear arms race. This has led William Perry, who's a former Secretary of Defense, to say in 2015, when things were a bit better, that the danger of some sort of nuclear catastrophe is greater than it was now. It's greater now than it was during the Cold War, and most people are blissfully unaware of this danger. So what does this mean? It means that government leaders are not now reducing this threat. It requires pressure from the public. And will bring us to our discussion maybe once we finish the colloquium, that what can the physics community do? And we believe that we physicists can play an influential role in advocating for steps for threat reduction. And we can play a role that can be more significant than other sectors of society. And so we formed this Physicists Coalition for Nuclear Threat Reduction. And I'm going to skip this now because we're going to discuss this for those that are interested a little bit later. I just want to say now that this is a coalition that gives all physicists, not experts, just a physicist who is interested, just as an informed physicist, it gives you an opportunity to advocate in an organized and effective way, orchestrated through the APS, to advocate for steps to reduce the nuclear threat. And we'll discuss that later. There are many ways to do this. So I want to quit now. We'll discuss that more for those interested once we stop. I'll just stop with taking a quote from an article that's now two years old, was an article in Physics Today on nuclear weapons. And I'll just quote the subtitle of the article, which is written by Steve Feder, Dick Garwin, and Frank von Hippel, and two of them are part of our coalition. And the subtitle says, with the end of the Cold War, most physicists turn their attention away from the nuclear threat. It is now time for us to re-engage in the debate over how to reduce the danger from nuclear weapons. So with that, I'm going to try to stop my screen share if I can. Let's see. And open it up to questions or discussions.